let's start. So today we continue with examples of quantum mechanical systems from the point of view of differential equations. And I would like to give you one more example, which is somewhat technically involved. But on the other hand, it will play a big role in the next topic. So that's why we look at it. Right, so we'll take the potential to be some constant times x. So the Hamiltonian is, as usual, the second derivative plus the constant times x. So we would like to solve the differential equation h psi equal to e psi for some value of e. And so this differential equation reads is what? Cx is it correct? Something like this. So now kind of we'll need those constants later on, but at the moment let's simplify it. So we can always shift the argument, and we can also rescale. So we can always eliminate all these factors. We can eliminate e, and we can eliminate all the other factors. So we can simply deal with this equation. So for all values of e, so in particular e just amounts to shifting of the argument x. So here I am assuming, say, for instance, c bigger than 0. C smaller than 0 can also be handled. Right, so this is a famous equation called the Airy equation. And I'll now write solutions to the Airy equation. Actually, it is convenient to consider it over a complex plane instead of a real line. And then, well, when we consider it over C, the usual notation is, instead of x, we use z. Right. Okay, so let me draw the complex plane, and let me consider the following integral as a function of z, so integral over some curve to be specified. And here we'll look at the following interestingly looking function. So exponential of t cubed over 3 minus t times z integral over dt. So actually, this will be the complex plane of the variable t. Now, note that this expression t cubed over 3 so let's look at this thing, and let's look at its real part. So for us, it will be important whether this real part is positive or negative. So of course, when t goes to infinity along some ray in the complex plane, if it is positive, it grows very fast, or exponential of it grows very fast. If it is negative, it decreases, and the exponential of it goes very fast to 0, right? So there are very, very different types of behavior of the function exponential of t cubed over 3. So let's draw it in the following way. So there are those interesting sectors. So this will be, I think, pi over 6 minus pi over 6. So then the next line, I think, is here. And there are two more lines like that. So now the complex plane is split into 6 sectors. Now what happens with this expression? Clearly it grows in this sector, and it's easy to see that it also grows in those 2 sectors. And it is negative in these 3 sectors. So now basically this part of the exponential factor, exponential of t cubed over 3, will very fast go to 0 if I go to infinity in one of the minus sectors, and it will blow up if I go to infinity in the plus sectors. So let me draw the lines somewhere, some rays, maybe in the middle, say. Oh, it doesn't matter so much. So let me draw the rays going to infinity in the negative sectors. And, well, we're a little bit running out of colors. We're a little bit running out. Okay, let me try this one. Tell me whether you can see it. So we're gonna draw 3 curves. So a curve will be coming from minus infinity in one of the sectors and going to the infinity in the other sector. So this will be this will be one curve. This will be another curve. And this will be the third curve. So let me call them C1, C2, and C3. So it's clear that the corresponding integrals, if I put in those curves, so the corresponding integrals are well defined. These are improper integrals, but the function under the integral, the integrand, it falls to 0 so fast at all the infinities that those integrals are very well converging. So let me state and prove a short proposition. So the functions psi 1, 2, 3 so where I choose either C1 or C2 or C3, thank you, as a curve, is a solution of the area equation. So maybe first a small remark. Recall that actually we are supposed to have two linearly independent solutions. We don't need three linearly independent solutions, but also it is easy to convince oneself that, for instance, the integral along the curve C1 is the same as the sum of integrals over the curve C3 and C2. Recall that we are actually on a complex plane, so we can deform, so the function is holomorphic everywhere, so we can deform those contours as we want. So actually we can retract this tail and deform the union, the sum of C3 and C2 to C1. So actually psi1 is equal to psi2 plus psi3. So proof. Right. So as I said before, the integral is improper, but it's so well converging, we can differentiate under the integral, whatever. We can do as if it were an integral over a finite interval. So psi double prime of z is 1 over 2 pi I integral, and then, well, the second derivative will give us t squared well, here we can do an elementary integration by parts if we remark that we can single out exponential of t cubed over 3. So we have here a t derivative, here exponential minus tz dt. Well, so after integration by parts, we get minus 1 over 2 pi I integral over c exponential t cubed over 3, and here will be minus z exponential minus tz dt. Of course, again, one should convince oneself that kind of the integration by parts works, but this guy falls so fast, it's no problem. So, and this is equal to z times psi of z. So we got three solutions, but they are related by this identity. So we got two solutions of the area equation, and in particular we'll now study the behavior of one of them. So the solution psi1 is called the area function. So the notation is like this. So this is just a piece of notation. And we'll be interested in the asymptotic behavior of this function when z goes to plus or minus infinity. So let me start with the plus infinity analysis. So let me denote the function here in the exponent. Let me denote it by f, or maybe better, let me say g of t and z, and it is equal to t cubed over 3 minus tz. Let me do the following small trick. So we decided z is positive, so it admits a positive square root. Let me say t is equal to z to the power 1/2 times a new variable tau. So this will give me z to the power 3/2 tau cube over 3 minus tau. So what happens with my integral? So I get a new expression for this area function. So it's 1 over 2 pi I. So the contour remains the same after rescaling of z. The directions, they are the same. Now here the exponential of z to the power 3/2, and here tau cube over 3 minus tau. And here will be d tau, and I still need to make a change of variables. So here will be, I think, z to the power 1/2 from the change of variables. Right, so that's a new expression that I want to study. Now I would like to make a small digression. I guess you probably know it, or maybe if some of you don't know it, let me recall how it works. So so let me recall some classical topic, Gaussian integrals and the steepest descent method. So first of all, of course, well, we all know, well, do we? So we all know that this integral is a square root of pi, right? Now, this implies that if we want to change a coefficient, let me do it this way. So a is some positive constant, right? So then the change of variables will give me the square root of 2 pi over a, right? So that's the first year calculus integral. Now, there is a following theorem. Suppose that f is a, let's say, smooth function from R to R. X naught is a global maximum of f, and we assume f double prime of x naught is strictly smaller than 0. So it's not, this maximum is not too flat. Of course, the second derivative might have vanished. So then the following integral is given by the following formula. So, so how does f of x look like near the point of the maximum? So it is equal to f of x0 plus 1/2 f double prime of x naught x minus x naught square plus, according to the asymptotic Taylor expansion, plus something which is O of x minus x naught cube. So now we'll be assuming so that the parameter s is large and positive. So then the steepest descent method is saying that this expression, this integral I of s, is given by exponential of s f of x0 times the following interestingly looking expression, square root of 2 pi s minus f double prime of x naught, and here 1 plus O of 1 over s. And we also assume that the integral is actually converging. So if we have a convergent integral of this form, so then basically this theorem is saying that you can essentially replace the function by the first two terms of the Taylor expansion. And this will give you the leading asymptotics for S large, and then the corrections will be of this form. So there will be the rest, there will be a narrow term, and divided by this factor, it will fall as 1, at least as 1 over s, when s goes to infinity. In fact, in this integral, so those limits are also negotiable. It's sufficient to have some segment around x naught, or it can be a semi-axis containing x naught, and x naught should be an interior point. So you can, in principle, negotiate those limits, so this theorem will be still valid. Okay, so this was a digression. Well, now look, we are actually more or less in the situation that I described before. So let me redraw. I will be redrawing several times the picture. So so here in this integral, our parameter s is z to the power 3/2, right? So that's our large parameter. And the function f of tau is tau cubed over 3 minus tau. Now, what are the critical points? F prime of tau. So this is tau square minus 1. And if you put it equal to 0, we have tau equal to plus or minus 1. And the second derivative is equal to 2 tau. Maybe it's also good for us to know what are the values of f plus 1 and f of minus 1. F of plus 1 is minus 2/3, and f of minus 1 is plus 2/3. Now let's do the following. Let's draw on the plane the places where the imaginary part of f of tau is equal to 0. So let me replace here tau by tau. And we would like to know what are the places where the imaginary part of this function vanishes. Well, first of all, let me mark those critical points. So this is plus 1, and this is minus 1. First of all, clearly on the real axis, right? Our function is real. So the real axis is the place where the imaginary part vanishes. Now, so what happens along those rays? You know, t cubed over 3 along those interesting rays. So here pi over 3 minus pi over 3, 2 pi over 3, and minus 2 pi over 3. So t cubed over 3 along those rays is real. Now tz or this tau, of course it's not real. However, this guy, the other guy, becomes so much bigger, so it's easy to find a place where it will be real. So somewhere here, roughly on those rays, so there are places where it is real. Now let me also draw the directions in which the function grows. Right, so the function grows here when we go to plus infinity, right? Now this critical point is a local minimum, right? So this means that the function grows when we go from plus 1 to minus 1. Remember, here it's minus 2/3, here it's plus 2/3, and it also grows here, right? Because it's minus infinite. So it also grows in that direction. It grows here, it grows there, and it grows there, right? Now, what happens at those points, right? So remember, we're dealing with a complex variable. So for instance, around here, the behavior, the first term of the Taylor series is what? So we have f of tau is equal to minus 2/3. That's the value at plus 1 plus 2 times tau minus 1 squared. Right? In particular, this means that if you go in exactly imaginary direction, right? So you will also remain real. Just it will be with a minus sign. So somewhere here there is something like this, and over here there is also something like that. Now, well, we're not going to prove it, but kind of now let's put together the picture. It actually looks something like this. So those lines connect, and those lines connect. So, and that's the set. That's roughly how the set where the imaginary part of f of tau is 0 looks like. So so there are those lines, and they intersect at the critical points. Now, why I'm telling you all that? Because you know this C, this integration quanta, you can choose it, right? Those directions are fixed, but otherwise you can choose it. So let's choose it as a line of imaginary of f equal to 0, right? So then it will be passing exactly through that point, right? So that point, and the function falls in those directions. It increases, right? We were drawing those directions such that the function increases. So the function increases from minus infinity, reaches the maximum at minus 2/3, and then it decreases again back to minus infinity. So actually it fits perfectly this steepest descent method conditions. So let's choose C to be that line. Well, Very good. So now what's the asymptotic of AI for Z positive? Well, it was a little bit of a struggle when preparing this class. There are, of course, all those formulas, right, that you can look at the books, but then you need to match them with the actual calculation. I hope I did it correctly or not. No. All right. So what do we have? So we have Z to the power 1/2 over 2 pi I, right? So that's the factor in front of the integral. Now there should be the exponential factor. So this one. So will be exponential of what? Of minus 2/3. That's the value of f times the parameter. This is Z to the power 3/2, right? So that's the S. Now comes that factor. So that's the square root. That's the square root of 2 pi. Here Z to the power 3/2. Now there is a slightly confusing point. Right here I should write minus f double prime. F double prime is equal to 2 times 1 is equal to 2. It's actually negative. However, you know, we are on the complex plane and we're going in that direction, which is a purely imaginary direction. So actually, that theorem was for a real integral along that line. So when you substitute it there and put tau minus 1 purely imaginary, sorry, here I think was over 2, right? To be honest. Because 1 over 2 factorial times the derivative, whatever. So you will get an extra minus sign. So the second derivative as a real function in that direction is actually negative. So times 2. So that's minus the second derivative. There is one more factor. You know, in this integral, we integrate over d tau. Tau is a complex variable. And at this point, our integration contour, it goes in a purely imaginary direction. So this means that from the change of variables, there should be another I. And, well, I think that's it. So then one all right. So let me try to write the correct asymptotic formula. So it is 1 over square root of pi z to the power, finally 1/4, 1/2 minus 3/4, exponential minus 2/3. Well, sorry for torturing you with this complex analysis exercise. In fact, the rest of this hour, the remaining 10 minutes, I will still continue torturing you. But maybe let's stop for 1 minute. Let me tell you which parts of the answer are important, which parts you should pay attention to. Actually, everything is important. I mean, like, okay, no, but let's say, please remember this factor of 2. Please remember this z to the power 1/4. It will come up. Of course, obviously, remember this and that. Well, more or less what you can safely forget is the square root of pi and this nonsense, right? So those things will not play a major role. All the other things will play a major role soon. Right. Okay. So now, in the remaining 10 minutes, I would like to maybe somewhat more briefly tell you how you get an asymptotic for z going to minus infinity. So what happens when z goes to minus infinity? So let me denote minus z by w, and this is a positive parameter. So it makes sense to rewrite the function as t cubed over 3 plus tw. And here we play roughly the same game. So I introduce the substitution. T is equal to w to the power 1/2 tau. So I'm getting a large parameter, w to the power 3/2. And here will be now tau cubed over 3 plus tau. So nothing much, just the sign changes. However, this change of the sign, it radically changes the picture. So let's see what happens. First of all, f prime is t squared, tau squared plus 1. So if we put it equal to 0, this will give two solutions, two critical points, plus and minus I, right? So f double prime is still given by the same formula. Now, of course, we'll have pure imaginary values of the second derivative. And finally, f of plus I, so this is f of plus I is equal to what? 2/3 minus 2/3? Tell me. Well, yeah, plus 2/3. Okay. So this requires a new drawing. So now the critical points are located at plus I and minus I. Now, unfortunately or fortunately, it's unrealistic to look at the imaginary part equal to 0, because at the critical points, the points that are most interesting for us, actually f is not real. It's actually pure imaginary. So therefore, we'll be looking at the lines where imaginary part of f is non-zero. It will be equal to 2/3 I, and let me draw in a different color, imaginary f minus 2/3 of I. So we're going to draw some of those lines. So in particular, let's first look at this, right? So the point plus I. So there the imaginary part is 2/3 of I. And we're interested what are the other places with the same property. how do the corresponding lines look around this point? So the second derivative is equal to I. So the square of your argument should be also pure imaginary in order to make the whole thing real, right? So, so if you don't want to change the imaginary part, you have to go at pi over 4 angle, 45 degrees. So this is how the lines of imaginary f equal to this thing, how they are passing near that point, right? Now, I tried to compute it, and in this direction it will be maximum, in that direction it will be minimum, right? There is, in the complex plane, you would always have like one direction along which you maximize the real part, along the perpendicular direction you minimize it, as we had before. Now, again, right, there was this idea that there were those special rays, right? There were those rays, the very interesting ones, right? So there were those rays where t cube over 3 becomes very large and real. Large positive or large negative and real. And we said that surely nearby we can find a place where the imaginary part is 0 for the whole sum. But now we can, in the same line of argument, we can find a place where imaginary part is whatever we want, whatever, 2/3 over I, whatever we want. So those lines reconnect like this. So that's the pattern of the level lines, imaginary f, 2/3 over I in the upper half plane. Now, a similar picture for imaginary f equal to minus 2/3 times I. So here again will be directions which reconnect like that, and how is it? So it has to come like this, and it has to come like that. So on this line it's a maximum of the real part, on that line it's a minimum. So that's how it goes. Okay, very good. Now what do we do with that? Recall that before we were arguing that psi1 is equal to psi2 plus psi3, right? Now it is convenient for us to use that fact because we can simply choose now the C3 curve to be this curve and the C2 curve to be that curve. So we can simply make that choice. Now, you see it's kind of interesting. So we're going to use again the steepest descent, but now there are two integrals and there are two critical. So before there was just one critical point contributing in our asymptotic behavior of AI. Now there are all of a sudden two integrals, there are two critical points, they both contribute, right? Because the quanta C1 is the same as C3 plus C2, and there is a critical point on each of them, so we can apply the steepest descent. Okay, so let me still spend 2-3 minutes of your time and write down the answer.
Sorry, doesn't this picture contradict the previous picture with imaginary part of f equal to 0?
Why?
Doesn't it intersect
But the previous picture was for a different function, right? So maybe it contradicts, but it actually doesn't, right? Let me erase the steepest descent. Yeah, you see, it's, well, of course, it's an elementary complex analysis, but, well, complex analysis is full of miracles and full of surprises. So, so let me so recall that z is minus w. So I will be writing the asymptotic in terms of a w. So psi 2. Let me write the expressions which come out from the steepest descent, and then we'll add them up. So it's kind of similar to the formula above. So here 2/3 over I 3/2. Right, so that's from a change of variables in the integral. So this is the contribution of the maximum. So then square root of 2 pi. Now I again make my I again tilt the contour such that the second derivative becomes minus 2. So, and this is minus the second derivative. And now an interesting factor, exponential of I pi over 4. And this is because now we integrate near the critical point, we integrate in the direction at pi over 4 with the real axis. So that's from the change of variables. And then, as before, and psi 3 will have a somewhat similar behavior. Maybe one small thing that I should comment on is that minus sign, right? So there is here minus sign. So that's because we're still integrating at 45 degrees. But remember that the integration contour goes from here to there in the psi 3 integral, right? So this is minus exponential minus pi over 4. Now, well, psi 1 of minus w is a sum of those two gadgets. And here is the formula. So 1 over square root of pi w to the power 1/4, and here sine of 2/3 w 3/2 plus pi over 4 1 . Right. So let me end this longish hour by the following comment again, right? So that's an important formula. And what is important about it? Well, the answer is the same. Everything is important. But what is super important? One super important point is that in contrast to this formula, there is no factor of 2 all of a sudden. And another thing which is super, super important, so this is this pi over 4. Right. So I'll give you a bit more comments. So we're going to keep this at least that blackboard, and I'll give you some more comments after the break. And after that, we'll dive in another topic where at some point we'll very heavily use those formulas. All right. All right, so let's continue. So let me still, before we erase all this beautiful stuff, let me say some words about it. Actually, this area equation and the behavior of its solutions, it's an entry point into a huge and actually very active mathematical field. So it goes under the name of the Stokes phenomenon. And just for your information, we are now running a kind of more or less a separate section of our seminar on the Stokes phenomenon. From time to time, maybe you see the announcements which are called the Stokes seminar. That's a research seminar about the Stokes phenomenon. Now, what is, roughly speaking, so we're not going to dive into it now, but roughly speaking, what is the Stokes phenomenon? So as you see, so the area function is one of the two solutions of the area equation. As we know, it's a second-order equation, so as every second-order equation, it has two linearly independent solutions. So one possibility how you can label linearly independent solutions is by their asymptotic behavior. Now, from the formulas here, you see these leading asymptotics. The main contribution is this exponential. So this exponential, which is in these three formulas, this one, and that one. And what we see there is whatever, 2/3, but forget 2/3, it doesn't matter so much. But then there is a function z to the power 3/2 with a minus sign or with a plus sign. Remember, w is minus z, right? So if you take minus z to the power 3/2, it will cancel that I. So this will be plus or minus z to the power 3/2, depending on which branch of the square root you choose. Right? So now here I finally renamed my complex plane into the z-plane. So I'm interested in what happens on a complex plane. So now in the exponential I have up to the multiple of 2/3 z to the power 3/2 and minus z to the power 3/2 in my solutions. And of course, depending on the sector of the complex plane, one of them, the real part, is bigger than the other. For instance, here on the real line, if we simply take the positive square root, so then z to the power 3/2 will be positive, and minus z to the power 3/2 will be negative. So for instance, this exponential that we got in AI, it's an exponential which is rather rapidly falling along the positive axis. So the other solution would be increasing with the corresponding exponent z to the power 3/2, right? So actually AI, you can characterize it as up to a multiple, up to a constant, the solution which has this asymptotic behavior along the positive real axis, right? Now, the naive intuition would be that as we go around the complex plane, as we change the direction, we should analytically continue that asymptotics. However, it turns out that this is not true. Because, you know, AI of z was defined by a globally defined integral, which is holomorphic for any value of z, positive, negative, anything. Now, okay, so we go around, and okay, we don't know what happens here. Actually, that's one of the exercises for next Monday, just to see a little bit what's going on there. But we know that when we arrive here, that's a mixture of both exponentials in equal proportion. So it turns out that when you analytically continue, the other exponential will jump in somehow. And that's maybe one possible way, maybe not the most clear way, but that's the way which is easiest for us today to say what is the Stokes phenomenon. So the Stokes phenomenon is this mixing of solutions with different asymptotics. So this globally defined AI, it has different mixture of those exponentials on different rays. Maybe one thing to say how it actually happens, just intuitively. So here, the exponential that we had was a smaller one. So we didn't have a bigger exponential. But when we pass to the next sector, that exponential becomes the bigger one, right? And once it became the bigger one, the other exponential may sneak in because we don't see it that much in the exponential behavior, right? So when we go along those rays, so actually the exponential that we have there will be rapidly increasing. And it turns out that the other exponential sneaks in, and at the border of this sector, where those exponentials become equal, you actually see it, that the other exponential came in. So that's roughly, very intuitively the thing. As I say, this Stokes phenomenon is a huge thing, both like in analysis, in rather abstract algebraic geometry, kind of in different fields. So kind of, and this is the first example of the Stokes phenomenon, which was discovered by Stokes, I think, himself. And so that's an interesting story. But now we want to dive, let's continue with quantum mechanics. So we could have spent like the whole course on the Stokes phenomenon, maybe taught by someone else, but so that's a big thing. So let me go to another topic. And you know, we are not approaching the end of the course yet, but the middle of the course is behind us. So now from time to time we should be talking about problems which are difficult or unsolved. So one of the interesting or difficult problems of quantum mechanics is its relation to classical mechanics. So up to now we were completely ignoring, right? We didn't speak about any classical mechanics. So now we're going to speak about classical mechanics, and we'll in some way rediscover it, starting from quantum mechanics. And it goes under the acronym WKB. And now let me copy the names because I don't remember them. So everybody knows WKB, but I think not everybody remembers the names. So it's Wenzel, Kramers, Brillouin. And the idea here is as follows. Let me try to introduce a setup. So as usual, we are looking at a time-independent Schrödinger equation for some potential. So we will be looking at it both as a differential equation and spectrally. And now we don't want to ignore the parameters, and in particular the parameter h bar. And we will be looking at the behavior of this equation when this parameter becomes very, very small. Now notice that this is a somewhat problematic region or somewhat problematic limit for the equation, because the parameter h squared is the coefficient in front of the top derivative, right? So this equation has some terms where we simply multiply the function by something, but this is the coefficient in front of the top derivative. Or if you rescale, you can divide everything by h squared. Then you will have a normal coefficient like of order 1 in front of the second derivative, but then these terms will have a huge coefficients 1 over h squared. So in principle, this is a difficult and in some way unpleasant or kind of challenging limit of this equation. Okay, so in fact, I will be specifically looking for the following situation for v of x. Let me perhaps draw it here. So we'll be starting for this complicated problem. We'll be starting v of x with some properties. So let's assume that v of x is some kind of potential well. So v goes to plus infinity when x goes to plus or minus infinity. So we assume that v prime over v and v double prime over v are bounded for x large. So somewhere out there, of course, here maybe it's difficult to arrange, maybe v is 0 somewhere, but we go far away. Next, maybe even more importantly, so we choose some range of energies between, say, E1 and E2. And we want the following. So for any energy E in the window between E1 and E2, we want the equation v of x equal to E to have only two solutions. So we don't want to be in that region to simplify things. So we want these two solutions. So we call them A of E and B of E. And furthermore, we want the derivative of the potential at A to be strictly negative and the derivative of the potential at B to be strictly positive. Notice that this means that in that window, the graph of V does look like this. So it is a falling branch on the left, and it is an increasing branch on the right. So most of these assumptions are just for technical convenience. But, well, as I say, this is a complicated problem, so we better be well framed. Now, there is some physics terminology. We'll see what is its meaning in some minutes, but let's introduce it. So the region to the left of A and to the right of B. So this is called classically forbidden region. So the region between A and B is called classically allowed. And the points A and B are called turning points. So that's the terminology. All right. So now in this topic, there will be two statements. One very simple statement that I'm going to prove, And then there will be a more complicated statement that I will try and possibly fail to explain. So there I don't make an attempt of proving it. So the simple statement goes under the name of a classical approximation. So let me, before introducing it, let me make a calculation. So I choose an ansatz for a function psi of x, right? So we're going to try to approximate in some way. In kind of, we will need to define kind of what does it mean to approximate, but we'll try to approximate solutions to that equation. So my ansatz will be as follows. I'll have two functions of x, a of x and s of x. S of x will be a real valued function, a of x more or less arbitrary, and we'll try to make an ansatz of this form. At the moment it looks a little bit meaningless because a of x is still anything, right? But we'll make it a bit more precise in a second. So let's try to substitute this ansatz into the Schrödinger equation and see what it gives. So I'll be computing h minus c acting on psi. So this is equal to minus h squared over 2m d2 over dx2 plus v of x minus e, and this is applied to this function. At the moment a and s are completely arbitrary. S is real. That's the only condition. Well, now I would appreciate if you watch my hands. I'll try to do it correctly, but you know it's hard. So what's going to happen? If I try to collect the terms with the same power of h, I think I will have v of x minus e plus 1 over 2m s prime squared times a of x. I plan to do the to put the exponential at the end of the whole bracket. The exponential clearly will be in all the terms, right? Now, minus IH over 2m minus IH over 2m, and here what? S prime of x, a prime of x plus s double prime a of x, and minus h squared over 2m could it be right? I think the chances are not very high, but
yeah, the coefficient for double S prime, S double prime, maybe?
coefficient, yeah, What about it? Is it good? So, opinion of the calculus experts? Well, here everybody is supposed to be calculus expert, right? Is it right? Is it not right? I don't know. No, I mean, and our future crucially depends on your judgment, right? Okay, let's say, when you find a mistake, tell me. I'll keep it for a while. All right, so there is this huge expression. Now, what can we make out of it? So the idea is as follows. We say h is small, even though, of course, we need to make it precise. But so we want the right-hand side to be 0, right? Ideally, we want to solve the equation. So for that, the left-hand side needs to be 0. Now, the right-hand side, h is small, and it has contributions of different order of h. At the moment, of course, it doesn't mean much, but let's try to follow that logic. So, so there is this, here there is an h bar, here there is an h bar square, here there is nothing. So this better be 0. And of course, right, s is at our disposal. So the idea is choose s prime of x equal to the square root of 2m e minus v of x. Here, let me note that the square root can have any sign. So that will be whatever, plus or minus, but we can include it in the definition of the square root. So we choose some branch of the square root. Actually, this right-hand side, we can introduce a special notation, because in the classical mechanics language, this is called a momentum. So note, it's actually interesting. So so p of x is real in the allowed region, right? So the allowed region is where v is smaller than e, right? So that's this region. And p of x is pure imaginary in the forbidden region. Right, because this expression is negative, p of x is pure imaginary. In that case, it will be convenient to introduce a different notation. A real valued square root q of x, right? So that's p of x is I times q of x, or minus I times q of x, depending on the branches of the root. And p of x is 0. For x equal to a and b. Now, maybe just a short comment. Just a short comment about classical mechanics. In classical mechanics, if you remember from your high school course or from your university course, the momentum is related by mass to the velocity, and this means that we obtain a formula, right, for the velocity, which is this 1 over m square root of 2m e minus v of x. But this classical mechanics story only applies to the allowed region. So the classical mechanics knows nothing about the forbidden region. So the picture that classical mechanics people have is that the particle moves with that velocity v, and if we choose the positive branch of the square root, it moves from left to right, it runs to the turning point, at the turning point the velocity vanishes, and then you go to the other branch of the square root, and then it returns. In fact, if we were developing a little bit more of algebraic geometric approach, we would have had a double cover of our complex plane. We would have a complex plane, a double cover, and we would go around two sides of the branch cut. So that would be the picture. But now in classical mechanics, the picture is that our particle should oscillate between two turning points with the velocity v, which depends on x and given by that formula. All right, so now let's try to make our story a little bit more precise. So let me formulate a proposition. So that's a proposition that actually I'm going to prove. And then I'll try to formulate a theorem that we're going to discuss next time. So, so there exists a positive constant and a smooth function a supported in the allowed region. Such that psi of x equal to a of x exponential I over h s of x. This s of x given by that integral. So of course, right, s of x should integrate the equation s prime equal to p. So that's one particular solution of it. Verifies h minus e psi bounded by c times h bar for the energy in the E1, E2 window. So we would like to prove, an estimate for this, for h minus e. You see, so that's a kind of more precise formulation of what we want to say. So we want this thing to be small. So small would mean that the L2 norm is bounded by something which is proportional to h with some constant which is independent of the energy. All right, so let's prove it. So first of all, let me choose this a of x. In fact, what we'll do, so let's choose the smallest allowed region, which corresponds to the smaller energy, E1. And let's choose any compactly supported C infinity function, which is equal to 0 near the turning points. So let's step away from the turning points a little bit, and then do anything. Any non-vanishing smooth function, it can have oscillations, whatever you want. And let's fix it. So we fix it once and for all. It no longer depends on h. So this is just a fixed function. So choose A. With support in the allowed region, vanishing near turning points. So now we're going to use this formula. So we have h minus e times psi. Have you found any mistakes in the meantime? All right. Well, then it's your responsibility, right? If anything happens, if it doesn't work, then no. So now this term that I erased it because of our choice of s, right? So we chose s such that this vanishes. Okay. Now what do we have for the estimate? Well, we're going to have a naive estimate for that L2 norm. So this is more equal. This is more equal than the L2 norm of this guy times this. The phase will always disappear, right? So it will be then h over 2m times the L2 norm of 2 p of x a prime of x plus p prime of x a of x plus the L2 norm of that guy h squared over 2m, the L2 norm of a2 prime of x. All right, so this guy is just some constant, right? I chose it to be C infinity, so that's just some constant, actually times h squared. Now this is also okay. P of x is a continuous function. Now this might be slightly problematic, right? P prime of x. So that's a derivative of some square root, and a priori at the turning points, near turning points, it is unbounded. However, we stepped away from the turning points in our choice of A, so A is actually equal to 0 near the turning points. And in the compact region, inside the allowed region, on this compact segment, P prime is also a continuous and hence bounded. So actually this term we don't care at all, and this term gives us a constant times h. So for h bar small, we obtain our estimate. Okay, so what does it mean? Now, so what does it mean spectrally? So the corollary of it, for every energy E in the interval, E1, E2. There exists a point in the spectrum of H such that the difference between them is smaller than C times H. So why is that? Maybe I'll leave it as an exercise, right? If this is not true, if the spectrum is further away than CH from E, right? Then first of all, E is a point of the resolvent set, right? Then there is an inverse, and you have a bound on the norm of that inverse. And that bound will simply contradict this, right? Sorry, here maybe I should say, maybe I should have added the norm of psi. So this would just change the constant. Right? The norm of psi is equal to the norm of A. So this would be So this would contradict this bound because you see now psi would be H minus E minus 1 of that guy, right? So and this gives a lower bound on the norm. So it would be contradiction if this were not true. So what does it mean? So let's try to draw this spectrum of H in that window. So this means that at least with the density, this CH, there should be points of the spectrum, maybe more, maybe everything, we don't know, but at least that. Because from every energy, it cannot be further than CH bar. Now, when you send H bar, remember, those things in our estimate, so this is for all H bar. So when H bar becomes arbitrarily small, so then the spectrum becomes denser and denser so with a step which is at most CH bar. So that's what it says. Okay. So that's a very, as you see, that's a very, very naive, very simple statement. Now let me end this class with a much more complicated theorem. And we'll be discussing that theorem next Monday. So theorem. Suppose that the energy E in the window E1 and 2 is such that the integral of P of x dx along the allowed region from the turning point to the turning point is equal to pi n plus 1/2 for n a non-negative integer. Anyways, I choose the branch of the square root such that this guy is positive. So then this cannot be negative. So it kind of. So Yeah, I would have to add something before. So then, there is a tilde in the spectrum of H, such that there is a constant times H bar square difference from the point of the spectrum. And of course, here in the beginning, I should have said that the statement of the theorem that there is such a positive constant such that for all energies in the window, this holds true. So this is called, so the energies E which verify these conditions. So already the condition is called the Bohr-Sommerfeld quantization condition. Actually, that's where the quantum mechanics started. So it was not a Schrödinger equation, it was not all this nonsense that I was teaching you up to now. It was this formula, which was basically one of the first formulas of quantum mechanics. And then, starting from that, they kind of basically backwards found all the rest. Right, so the solutions to this formula, right? So there will be only certain energies for which this is true. So the corresponding energies satisfying Bohr-Sommerfeld are called Bohr-Sommerfeld spectrum or quasi-classical spectrum. Let me finish with the following picture, explaining what's going on. So, or maybe we will drawing the spectrum like this. This is classical. This is what is called semi-classical. So that's E1 and that's E2. And then, so our classical calculation was saying that between E1 and E2, there are those spectral points at the distance small or equal to CH bar. So my H bar, of course, has to be small, but here H bar square will be even much smaller. That's why I have to make the picture like that. Now, the semi-classical thing is telling you the following. So there is this semi-classical spectrum, right? So these are some fixed values of the energy for which this solution, this equation is solved. So the energy solves this equation. So these are the semi-classical. So this is sigma semi-classical or quasi-classical, whatever the word. Now, this theorem is saying that near each of them there is at least one, maybe more, who knows, point of the true spectrum with a distance now estimated by CH square. But CH square, when H is small, is much, much smaller than CH. Right? CH is kind of course, CH is very small comparison to the window, but comparison to ch squared, it's huge. So this is a much more precise statement on where this spectrum will be located. As I say, so we have no hope to prove this result here, but next time we'll probably spend maybe the first half of the class trying to understand what's the logic behind that result and how it is related in particular to the area functions that we were discussing earlier today. Okay, well, that's it for today.